If you've spent any time at all in the world of large language models, there's this fundamental tension,
Mm.
speed versus quality. It always feels like you have to pick one.
You do. I mean, that's been the physics of LLM serving for a while now. You push for that blazing fast inference, that high throughput, and your quality usually takes a hit.
And if you want that perfect high-quality output, you watch your GPU utilization just, tank.
Exactly. But today, we're diving into an architecture that really claims to break those rules.
Okay.
We're talking about TiDAR. It stands for Think and Diffusion, Talk and Autoregression. It's a really innovative hybrid architecture from researchers at NVIDIA and the University of Chicago.
And our mission for this deep dive is to figure out how TiDAR does what seems, frankly, impossible. We're talking about getting both high throughput and the quality you'd expect from a top-tier autoregressive model.
Right. And the numbers they're reporting are, well, they're huge. Speedups between 4.7 and almost 5.9 times over a standard AR model.
Wow.
So yeah, we really need to unpack this. We need to look at the core problem first. Why current models fail, and then really get into how TiDAR's specific design gets the best of both worlds in a single GPU step.
Okay, let's unpack this. So let's start with the basic limitation here, which is speed. If you're running a standard LLM, it's almost certainly an autoregressive model, an AR model.
Right.
They generate tokens one after the other, sequentially, like typing a single letter at a time every single time.
And that sequential process, that's the massive bottleneck, especially at small batch sizes. From a hardware point of view, we say these models are memory-bound during decoding.
Okay, so break that down. What does memory-bound actually mean here?
It means the GPU spends way more time fetching the model weights and the KV cache from its memory from VRAM, which is a relatively slow process, than it does actually doing the math.
So the part that GPU is actually good at, the number crunching, it's not doing that most of the time.
Precisely. It's just sitting there waiting for data. You are not fully utilizing the incredible compute density these modern GPUs offer.
So researchers naturally look for an alternative.
Of course. And they looked at diffusion language models, or DLMs, because they had this promise of decoding lots of tokens in parallel all at once.
But there was a catch, right?
Yeah.
Why didn't diffusion models just take over for text generation?
There was a huge catch, a really critical quality versus parallelizability trade-off. The best quality you could get from models like Dream or Lada, it often required them to decode just one token per step anyway.
So that completely defeats the purpose. You lose the whole parallelism advantage.
You lose the entire advantage. And if you tried to generate a whole block of tokens at once, the output quality just plummeted.
Why? What causes that quality drop?
It comes down to something called the intra-step token independence assumption.
Okay.
Basically, when the DLM tries to predict, say, 10 tokens at once, it treats them as if they're independent of each other within that single step. It damages the coherence of the whole sequence, especially for complex stuff like writing code or, a math proof.
So we're stuck. We need that step-by-step logical quality of AR models, but we desperately want the parallel speed of diffusion.
And that is the zero-sum game that TiDAR is designed to get out of. This is where the architectural breakthrough really happens. TiDAR is a sequence-level hybrid. It performs parallel token drafting, that's the thinking and diffusion part.
Right.
And it also does high-quality verified sampling, the talking in autoregression part, all within a single forward pass, a single NFE or network function evaluation.
And the core insight here is so clever. It's not just new math. It's a systems design hack. It's based on this concept the researchers call free token slots.
This is the core efficiency insight. So let's go back to that memory bottleneck.
Okay.
If you're stuck waiting for the model weights and KV cache to load, that wait time is pretty much fixed. The researchers realized that if they added a bit of extra computation, a few extra tokens to process to that single forward pass, the total time, the latency, it barely changes.
Because you're still just waiting on that slow memory load anyway.
Exactly.
So it's like if you're stuck in traffic, the total time is determined by the car in front of you. TiDAR uses that waiting time to do a bunch of productive work inside its own car.
That's a great analogy. That idle wait time becomes productive compute time, and those extra tokens you process during that time, those are the free token slots.
And TiDAR is built specifically to exploit them.
Engineered to exploit them, yeah.
Okay.
Turning a memory-bound process into a compute-dense one.
So we have to get into the mechanism. How does it do both the thinking, the parallel draft, and the talking, the sequential check at the same time?
It's a really sophisticated bit of engineering with these specially designed structured attention masks.
Okay.
These masks let the model work with two different probability distributions at once.
Hmm.
You have the high-quality causal one, the PAR,
Right.
gives you clean sequential output.
That's the talking.
That's the talking. And then you have the rougher marginal one, PDEF, that lets you draft a bunch of tokens in parallel. That's the thinking.
So how does that play out in a single computation cycle, that single NFE?
Okay, so two things are happening simultaneously. The parallel drafting, the thinking part, generates a block of proposed future tokens using that diffusion approach. At the exact same time, the tokens that were drafted in the previous step are verified or rejectively sampled in an autoregressive way using that high-quality PAR distribution.
Ah, I get it. So you're drafting the next block of text while you're verifying the block you just produced.
Precisely. And that's what dramatically increases your compute density. You're outputting so many more high-quality tokens for every single cycle the GPU runs.
That's brilliant.
And there's a huge practical advantage here, too. TiDAR supports an exact KV cache. This is vital.
Why is that so important?
Well, a lot of other diffusion models can't do this properly, so they end up wasting a ton of computation. By integrating that causal AR component, TiDAR avoids all that waste, which gives it a massive edge over methods like, say, block diffusion.
Okay, so this is where it gets really interesting because the engineering translates directly into performance. Let's look at the benchmarks.
The numbers are, well, they're undeniable. The TiDAR 1.5 billion parameter model. It achieved a 4.71 times relative throughput speedup over its base AR model.
4.7 times. That's already huge.
It is, but then they scaled up to the 8 billion parameter model, and TiDAR hit an incredible 5.91 times speedup.
Wow. Nearly 6 times faster. For anyone running a high-volume app like a chatbot or a coding assistant, that means your GPU serving costs just got slashed. That's the real bottom line here.
It absolutely is. But here's the most critical part, the quality.
Right, because the speed is useless if the output is bad.
Exactly. And the sources confirm that at the 1.5B scale, TiDAR is the first architecture to completely close the quality gap with pure AR models.
No quality loss at all.
None. And at the 8B scale, it showed only a very minimal loss, all while spitting out, on average, between 7 and 8 high-quality tokens in every single operational cycle.
So how does this stack up against other acceleration techniques? What about other diffusion LLMs?
TiDAR consistently outperforms them. Models like Dream, Lada. TiDAR is better on both efficiency and quality, especially on hard tasks like coding and math, where one little error can ruin the whole thing.
That AR verification step is the real difference maker.
It's the secret sauce.
What about speculative decoding? That's the current state of the art, right? Where a small, fast model drafts tokens and a big model verifies them.
TiDAR beats the efficiency gains of even SOTA frameworks like EGL3. And the reason is overhead. In traditional speculative decoding, you have two different models running in two sequential steps. TiDAR gets rid of all that sequential overhead because the drafting and verifying happen in parallel, inside the same model, in one step.
So it's like a self-speculative model all in one package.
Exactly. The paper gives 3 reasons for the edge. 1, the draft model is the base model, so it's high capacity. 2, the drafting is fully parallelized with diffusion. And 3, which is the big one, drafting and verification run side by side in one GP cycle. It's a massive efficiency win.
It's clear the architecture is brilliant, but you can't just get a model to do 2 things at once without some very smart training. How did they teach one model to both think and talk?
They needed a very specific set of rules for the model's attention mechanism. That's where this structured, causal, bidirectional hybrid attention mask comes into play.
Yeah, okay.
This special mask lets the model calculate both the autoregressive loss on the prefix, the sequential part, and the diffusion loss on the appended tokens, the parallel drafting part, at the same time from the same data.
So it's learning to be a great sequential predictor and a great parallel drafter simultaneously.
Yes, and they also used a really fascinating, almost counterintuitive training strategy. They called it the full mask strategy.
Oh, mask.
Yeah, instead of just masking out some of the tokens in that diffusion section, they masked all of them.
Why would you mask everything? Wouldn't that hide the signal?
You'd think so, but it was actually hugely beneficial. It provided a much denser diffusion loss signal, which really improved quality, especially in those tough areas like coding.
Yeah.
Plus, it simplified the whole training process and made it easier to balance the two loss functions. And it created better consistency between how the model trained and how it actually performed during inference.
And at the end of the day, when it comes to the final output, that talking part, the AR rejection sampling, that's the ultimate quality guarantee, isn't it?
That's the final gatekeeper. It's like you generate a rough draft very, very quickly, and then you have a world-class editor instantly check every single word before it goes out.
That's a great way to put it.
The ultimate quality is absolutely guaranteed by that autoregressive verification step. The researchers even tested this. They could tell the model to trust AR more or trust diffusion more during sampling, and the final quality was preserved either way.
So the key takeaway is that the rejection sampling is what holds that quality ceiling in place.
It is the non-negotiable step.
This entire deep dive, it really does show a new path forward. So what's the core takeaway for you, the listener, from all this?
Well, the breakthrough is that TiDAR successfully combines two totally different innovations. You have a hardware insight exploiting those free token slots,
Right.
and you have a very sophisticated software innovation, that single forward hybrid attention mask. And together, they finally bridge that gap between speed and quality.
It makes it a perfect solution for latency-critical apps where you need great throughput, but you just can't compromise on the quality of the output.
It's the difference between your GPU waiting on you and you actively using its full potential.
Exactly.
And here's the final provocative thought to leave you with.
Okay.
The researchers achieved these incredible speedups, that 5.91x gain using just native PyTorch, no custom low-level optimizations.
Really, so it's all just out-of-the-box stuff.
Pretty much. And they noted they can already adjust the draft length on the fly, in a zero-shot way to fit different hardware profiles.
So if they got this much of a speed up without even specializing the implementation,
The question is, how much faster could this get? How much further could that throughput be pushed if TiDAR were optimized with custom attention kernels and scheduling algorithms designed specifically for the hardware it's running on?
so you're saying these numbers, as impressive as they are,
They might just be the floor, not the ceiling.
Huh.
That next level of optimization could unlock even more performance. It's something to mull over.
that is definitely a powerful possibility for the future of LLM deployment. Thank you for walking us through this.
My pleasure.
And thank you, the listener, for taking this deep dive with us. We'll see you next time.